Oh, now I want to explain a very, very beautiful article, a unified linear time framework for sentence-level discourse parsing from a very good professor in Singapore, very good researcher. And you see, Salesforce is also using this in their research, and they use it in their products. So we have encoder, but you have a different decoder for segmentation, a different decoder for parsing, but it shares the same encoder. This is beautiful. It's like continual learning. It's like multitask learning, that you have a bunch of tasks, but you have a shared layer as well. So in that sense, it is just similar to that idea. So our segmenter yields F1 score of 95.4, and parser achieves F1 score. So parser has a little bit more problems. Has a problem because it is more difficult than just segmenting. Segmenting into discourse units is relatively easier. And the article uses pointer networks. And this is, you see the citations, 2,500. So many people have used it. Maybe in that combinatorial community, because this is more like combinatorial, you will see. I will explain at the end of this lecture. But what is discourse parsing? As I said, you have a kind of relations. You have, for example, this is nucleus, this is satellite. So it has nucleus and satellite. And these are elementary discourse unit, E1, E2, E3, E4. And so this is discourse. And the segmentation is that you're segmented. This is the boundary of the for this EDU. This is the boundary. I mean, the last word of this EDU. This is the last word of this EDU. So the next EDU starts from here, and so on. So transition-based parsers build the tree incrementally, as I said, by a series of shift-reduce actions that I explained in the previous lecture. The advantage of this method is that the parsing time is linear with respect to the number of EDUs. The limitation, however, the decision made at each time is based on local information. Yes, it's the same argument for independency parsing. We have two approaches: transition-based, which is very linear, very fast, but it's very local. The other one is graph-based approach, which is much more powerful, but the computational complexity is huge. So this argument in independency parsing, you can also use it for discourse parsing, no problem. In graph-based, they call it chart-based, the same idea. And you see the order of the computational complexity is huge in comparison to linear complexity. And what are the pointer networks? You see that instead of 1, 4, 2, 1, it's pointing to the first word. It's pointing to the fourth and second and one, the first one. But you see that it depends on the number of sentences. So you cannot learn it. It's not scalable. That's why they created the trick like this, such that you use the embedding of that. And these are attention. These are attending to that. And I will explain it later. For example, they use it for this convex hull approximation. You have a bunch of points, and you want to see what is the convex hull of that, and you calculate it. So we go from 1 to 4, then you go to 2, and you go to 1 again. So here is the 1, 4, 2, 1. If you give 1, it gives you 4. 4 again comes here. You give 4, it gives you 2. Again comes here, 2, 1. So this is the pointer network, so easy. But attention is a pointing mechanism. So you say, what is the probability that you attend to the fourth word? And this is the scoring function for attention. Sigma is the scoring function for attention. So we use this for both segmentation and parsing. I will explain. So, of course, you have a parent and sibling. So if you want to put this you put it inside parents and sibling. That's why you represent it like this. Parent, sibling. And discourse parser relations could be, for example, phi is the probability of between one span and another span. So, and the relation could be attribution, it could be condition, it could be joint, background, comparison. And because it's a kind of probability, for example, what is the probability that the relation between this span and this span is attribution? What is the probability that the relation between those two spans is condition? What is the probability that the relation between those two spans is joint? And you do it for all time steps. So relation classifier phi theta is between two spans. You want to learn it. And you can train this jointly. I mean, segmentation and parsing could be trained jointly. And the encoder is just by GRU. It could be LSTM, anything. And the decoder, I will explain what is the decoder. But you can also use dot product for the scoring function, because this is the hidden states of decoder. This is the hidden states of encoder, and you just need a dot product to get a number, and then that number you give it to activation to get another number. And you need relation classifier. So labels could be attribution, condition, joint, background. And here you have a span. So according to this span, you have a CK. And this is label specific feature. So between CK and CJ, of course, we are using exponential linear unit, this one. This is exponential. Instead of, for example, tan H or ReLU, we use here ELU for some good properties. So it takes two spans, EIK and EKI, and says what is the relation, what is the probability of any relation. So it takes two spans, for example, one span and the other span, and you represent it by some feature, because you are also learning some parameters, and you learn you learn them, and that's it. You can classify it. But as I said before, giving it to the decoder, you should represent it as a matrix. So each one is like, you give it like this. You just augment this parent. For example, if you want to give E point 4 to 6, here you want to know what is E4 to 6. You should give the parents first. I usually say that parents, imagine like this: parents minus sibling is what you are giving to. what you are giving to at the middle. So this is how you represent it. Why do we need this? Because there should be a way to see the relations between, to represent a tree. To represent a tree, you need a way, and this is an approach to represent it. I can't think of any simpler approach, so I think the authors use the natural, the most natural, and the simpler things that comes to the head. And of course, instead of matrix M, you represent it by this. And then feed it to the decoder. So we feed it to the decoder here, and then according to that, we are learning. So it's kind of, I've heard about it in the literature, I've heard forced learning. Yeah, I think it's kind of forced learning. Training loss. So as I said, first you should know the structure of your tree, and then also the label loss, because each one has a different relation label. And we always use L2 regularization to avoid overfitting and those kind of stuff. And our parser is trained to minimize the sum of loss for building the right tree structure and the loss for finding the correct labels. So we have a decoder for segmentation, decoder for parsing, as I said. So at each time step, decoder receives an encoder state corresponding to the first token. It produces a decoder state, which is in turn used to compute a distribution or attention. This is how pointer networks is used, because we are computing the attention to say that what is the probability that this is used, what is the probability that this is the end of we are using it for discourse segmenter. What is the probability that this is the boundary? What is the probability that this is the boundary? So the red ones have higher probabilities. For example, if we give H1, H3, X2, the second word is this is the boundary, so we should start from next one. X3, which is H3, they represent. Of course, they used the representation, but in their previous work, I mean, it was segbot. I will explain in the next lecture. They used it for the in the segbot. They used they just feed the input, not the hidden state of the input. So it's slightly different, but almost the same. So we've trained the model by minimizing the pointing loss and, as I said, this regularization, L2 regularization. Of course, you can do it end-to-end because segmentation is different from parsing. This is parsing, this is structural label, and this is L2 regularization. So theta denotes the parameters of our joint model. So a quick review of pointer networks in 2017, lots of citations. So a class of problems such as the number of target classes in each step of the output depends on the length, as I said. That's why we need this kind of PTR networks, because it uses an attention as a pointer to select a member of the input sequence as the output. And so attention tells what is the probability that this one is your. What is the probability that this is the boundary of element, for example, in the previous application? What is the probability that this is the boundary of that discourse unit? So sequence to sequence, so C is just a sequence of indices. For example, between 1 and n. But you need content-based, you need attention. Because if you represent it like this, you can understand that you can define the probability by just softmax of u, that is attention.